As I discussed in this chapter, the ranks of these four matrices are exactly the same. So A transpose times A, and A times A transpose. It doesn't matter if A is square or non-square. It doesn't matter if A is full rank or reduced rank. The ranks of all of these matrices are exactly the same. Now, it's important to understand the reasons why that is the case. You can explain this using SVD, which I talk about later in the book. It can explain this using the rank nullity theorem, which I also discuss in the book. It's related to matrix spaces and so on. But the purpose of this exercise is to demonstrate this empirically. So what you want to do is generate random matrices and specify the code, set up the code so it's soft coded so you can change the size and the rank of A, and then you compute and print out the ranks of all four of these matrices. And that's what I will show you now in Python. So here you recognize this code, of course. Here is where I create the matrix A as an M by N matrix of rank R. And those three variables are specified here. And then I compute, so we already have A, so I compute A transpose times A, and A times A transpose, and then print out the four ranks of those four matrices. And as I stated a moment ago, they're all the same. Now, I encourage you to play around with this. You can change this to be, let's make this be 18 and how about 7? So now you'll see that the ranks of all four of these matrices are 7. Again, it doesn't matter if A is tall or wide or square. It doesn't matter if it's full rank or reduced rank. The ranks of these four matrices will always be exactly the same as each other.